Swayam Prabha. Digital India. Educated India.
So you see, we are trying to prove the four-vertex theorem, and what we have done so far is that you see we are assuming that your curve has two or three vertices. Okay, remember that two vertices are always guaranteed. Namely, 2 points where the curvature the curvature has a local maximum and a local minimum. In fact, a global maximum and a global minimum. There are two such points. So two vertices are always guaranteed. And then you have to worry about the situation where there are three vertices. And the third vertex, if it is going to be, local maximum or a local minimum, then it will introduce one more vertex, okay, and you will get four vertices. So you assume that the third vertex is a point of inflection for the curvature, the sine curvature, okay. And then what we have proved is that in any case, the curve can be divided into two segments, so that the sine of this derivative of the sine curvature, that is opposite on these two segments, okay. And so the points that are used to divide the curve into two segments, we are calling those points as P0 and P1. So P0 is this point here, and P1 is this point here, and these are the 2 points where the curve is broken into two segments. From P0 to P1, the sign of the curvature, the sign of the derivative of the curvature is positive, greater than or equal to 0. Okay, and from P1 to P0, if you go, of course, always in the anti-clockwise sense, the sign of the derivative of the curvature is negative. Okay, so there are two segments of the curve where the sign of the derivative of the curvature are the signs are opposite. Then what you do is that you cook up another function which has opposite sign on these two segments of the curve. And the idea is that if you have two such functions, each of which has opposite signs on two segments of on the two segments of the curve, you take the product of the two functions, that will have the same sign throughout the curve, and therefore the integral of such a function, if it is not identically 0, the integral can never vanish. So how do you get the other function? So what you do is that you take this point P1 and then you take this point P0, okay, which separate the curve into two segments, and then you look at this line L, which passes through P0 and P1, all right. And what you do is that perpendicular to this line, you take this unit vector u cap, all right, and then start looking at the dot product of for any point P on the curve, you take the vector P naught to P, which is just gamma s minus gamma s naught, okay. You take that vector, which is actually this vector, okay, and you dot it with this unit vector here, okay. Now when P lies on one side and when P lies on the other side of the line, on the curve, then you see that these dot products have opposite signs. So what you do is that you take this dot product, this is P0 P1 vector, okay, you dot it with u, you see that on the two segments it is of opposite sign. So what you do is that you take that function and multiply it with the derivative of the sine curvature, which also has the same property that on two segments of the curve it has opposite sign, so that this product when you multiply it, it has the same sign throughout the curve, and it is not identically 0. So you see, if you take if you integrate that function over the whole curve, this integral is not 0. So what we are going to do is that we are going to use the Frohn's array to show that the integrand is actually the derivative of function, and therefore by the fundamental theorem of calculus the integral will be 0, because this is a closed curve, okay. So here is where the Frohn's array is used. So what we do is that, you see, so write this integral using parts. So integrate using parts, okay. And so when I do that, so let me remove some of these, okay. So what you do is that, you take so you take this, so you take this, as dv, and you take this as u, capital U, okay, and you integrate it by parts. You will get uv minus integral v du. This is what you will get. So basically, so you see v, so dv is ks dot therefore v is just ks, all right. So you will get gamma s minus gamma of s naught, this vector dot u cap, that is the u vector, that is the scalar function u. Then I have to write v, but dv is ks dot, so v is just ks, so I will get ks. So let me write it on the right side, u times v. So this into, I will get ks of gamma of s, okay, and then I have to put the limit 0 to L of gamma, okay, minus integral of v du. So I will get ks sub gamma of s, that is v, and du is, I have to differentiate this, okay. If I differentiate this, notice that u cap is a constant vector. Therefore, I only have to differentiate gamma s minus gamma s naught. Gamma s naught is also a constant vector, so I will just get gamma dot of s. So I will get gamma dot of s, where of course dot means d by ds. Okay, so I will get gamma dot of s ds, and I will get from 0 to L of gamma. Okay, now you see the sine curvature function is continuous on the whole curve, and s equal to 0 and s equal to L gamma are the same point. Therefore, this will go away. Okay, therefore you are left with only this term. Okay, and but you see this term, this gamma is actually t cap. Okay, so gamma dot of s is just t cap sub gamma of s. Okay, this is the you see gamma is parameterized by arc length s. Therefore, it is a unit speed parameterization. So actually norm gamma dot is 1, and gamma dot is therefore the unit tangent vector. Okay, and if you take the unit tangent vector and multiply it with the sine curvature by the Frohn's array relation, this is just the negative of the derivative of the sine normal. Okay, so the Frohn's array are it is t cap gamma dot is equal to ks gamma n cap s sub gamma, and n cap ns sub gamma cap dot is equal to minus ks sub gamma into t cap sub gamma. Okay, so these are the Fronius array. So you see this ks gamma into t cap. So I can so I mean only the integrand. So this one, this is going to be minus n cap dot, and therefore you see, therefore this is going to be minus integral 0 to L of gamma. I'll get minus n gamma cap dot s ds, but you see this is a dot, so it's a derivative, and by the fundamental theorem of calculus it's just, it's n gamma, n cap gamma at L of gamma minus n cap sub gamma at 0, and that is of course 0. So this is equal to 0. Oh, I forgot the u cap. What did I do? I should have, oh, there is a dot u cap. So sorry, yeah, I should write that. So this is, so I'll end up with, so I will get k, so I will get, I have to write v du. So v is ks, ks sub gamma of s, that is your v, and du will be gamma dot of s dot u cap, and then I'll have a ds, all right. And now of course this is a scalar, I can club it with this vector, so it will be minus integral 0 to L of gamma, and this is going to be minus ns gamma cap dot of s dot u cap, ds, okay. And this is now going to be, so I'll get 0 to L gamma. So this is d by ds of, I can write it as ns sub gamma cap of s dot u cap ds, okay, because u cap is a constant vector. And now apply the fundamental theorem of calculus, you will get ns cap sub gamma of L gamma dot u cap minus ns cap sub gamma of 0 dot u cap, and this is of course equal to 0. That's because the starting point is the same as the ending point, and everything is continuous. Okay, so therefore the moral of the story is that you see this integral, if you actually calculate it using using parts, and you apply the Fronius array relation, you get it as 0. On the other hand, we already know that it is not 0, so that's a contradiction. Okay, so this contradiction, the contradiction shows that the assumption that gamma has fewer than 4 vertices is false, and that is the end of the proof. So it will have at least 4 vertices, right? So it's a pretty simple proof. Okay, but the proof is kind of it involves geometry, so it is inspired by a picture, all right. So this is the proof of the Four-Vertex Theorem, and the case that we have used is the case of a convex curve. The convexity is very, very important because you are getting that that line which breaks the curve into 2 segments, where the the derivative of the curvature, sine curvature, has opposite signs. So that is very critically used. But the general proof of the Four-Vertex Theorem is also true in the general case when the curve is not necessarily convex. Okay, so there is a proof which involves more of geometric reasoning than the use of any differential geometric things such as the Fronius array relations. So there is a proof due to Osserman. So I'll let me also explain that proof. Okay, so geometric proof. The geometric proof due to Osserman for a general, non-convex, curve. So that is a geometric proof. Yeah. So so when you are looking at so now you have a simple closed curve again, and assume that the curvature function is continuous, all right, and now the curve is not necessarily convex, and you would like to again show that it has at least 4 vertices. Okay. So this proof does involve looking at the curvatures at various points on the curve, of course. Okay, but doesn't involve anything more. It's a proof where you use geometry. So so the idea is as follows. So let me explain the geometric idea of the proof. So you see, so you start with gamma, a simple, closed, smooth. Uh, uh, so C2. Let me put it as C2 smooth. You know, at least, so that I can talk about the curvature function at least as a continuous function. Okay, and but not necessarily convex. Okay, so you see the idea is that you're looking at a curve which is not necessarily convex like this. Okay, so a curve might look like this, all right, or it might look even more complicated. Okay, or even like this. So let me draw some. Okay, so you can have a curve like this, and these are all non-convex curves. Okay, and you would like to give a geometric proof in this case. Okay, of course, if you draw such a curve, you can physically see that there are at least 2 vertices. But the point is you have to give a geometric proof. So what you do is, the trick is that so the idea of Osserman is that you have to look at what is called the smallest circle that encloses and touches the whole curve. Okay, so you can see that you can do the following thing. So for example, in this picture, probably I will get a circle like this. Okay, so I'll get a circle like this, and similarly, maybe in this case also you'll get a circle. Oops. So you'll get a circle like this. Okay, and maybe here I'll get a circle like this. Okay, so so look at the smallest circle which encloses gamma and of course touches gamma. Okay, so that means that gamma, all the points of gamma are contained either on the circle or in the interior of the circle, and you choose among all these circles the smallest one. Okay, now so let us call this circle as C. Okay, so let me call it as C, and then what you do is that of course it will touch gamma. Okay, so this and touches gamma is something that it will be automatic. If you just look at the smallest circle that has gamma inside it, okay, then the smallest one has to touch gamma, because if gamma is completely in the interior of a circle, then you could shrink the circle to make it smaller. Okay, so the interior of the circle is an open set. Okay, and if no point of gamma touches the circle but all the points are inside, okay, then I can further shrink the circle and make sure that I get a smaller circle. So if you look at the smallest circle, if you take a smallest circle, that contains gamma, then it has to touch gamma. Okay, so let me write that any smallest circle which contains gamma either partly in the interior and partly on it. So I will say, let me not put either. So when I say circle contains gamma, points of gamma can lie in the interior of the circle, and some of them can lie on gamma themselves. Okay, has to, such a circle has to touch gamma. Okay, so this is a remark, right? And essentially this uses the fact that it uses the openness of the interior of a circle. Okay, so and which is a topological thing. All right. Now the question is, so what we want to really look at is these points where the circle touches gamma. Okay, so let me write this, look at C intersection gamma. So this is very, very important. Look at and note that C intersection gamma is non-empty, as I have told you above, because if no point of gamma touches C, that means gamma is completely in the interior of C, and then I can shrink C to get a smaller circle, and that contradicts the fact that C is one of the smallest circles that contains gamma. Okay, so so the points of C intersection gamma, I mean, these are topologically these are closed sets. Okay, because the curve is a closed set by definition, and the circle is also closed. Okay, and the intersection of two closed sets is also closed. Okay, therefore these are this intersection is it's a closed set which is contained on the circle. Okay, and in fact actually it's even compact because everything is closed and bounded. You see the curve gamma is the continuous image of this closed and bounded interval on the real line, which is compact by the Hein-Borel theorem. Okay, and the continuous image of a compact set is compact. Therefore, the curve itself is a compact set. It is both closed and bounded, and the circle is also one such curve. So it's also compact, and the intersection of compact sets is also compact. Okay, so the important thing is that this is a closed set. Okay, topologically it's a closed set, and what it means is that you take a point outside the intersection of the circle and gamma. That is then there is a whole open disk surrounding that point, which is also in the complement of the intersection of the circle and gamma. Okay, now so here is the first claim. So in this picture, So you see in the picture, if you look at the picture, you see I am interested in these points. So let me mark those points. See, I am interested, for example, here I am interested in this point and I am interested in this point, okay. And then sometimes it may happen that, you know, an arc of a circle itself is, you know, there on the curve gamma. So we would like to discount such a case in general, because if you know, the curve contains an arc of a circle or an arc of a straight line, then throughout that arc you have infinitely many points where, you know, the curvature is constant. So the derivative of the curvature is 0. So all those points are critical points and you get infinitely many critical points. The point is that you want to show that there are at least 4 critical points, okay, 4 vertices. The critical points of the curvature are the vertices, okay. You want to show that there are at least 4 vertices. So one doesn't want to really worry about the situation when a portion of the curve contains, you know, an arc of a circle or an arc of a straight line, okay. But that was also the assumption that we made when we were looking at the convex case, okay. So for example, in this picture, then I will be interested in this point and say this point here, okay, and in this picture I will be interested in this point and this point, okay. So you are looking at these points, you know, where you have the intersection of the curve with the circle, okay. So this is gamma and this is circle C. Okay, and so the first statement that one wants to make is that, you know, this so this set of points common to C and gamma, the claim is that it cannot lie in an open semicircle of the circle, okay. So claim 1, so these are geometric claims, okay. Claim 1, C intersection gamma cannot entirely lie on an open semicircle of C, okay. So basically the picture is that, you know, you have this C, okay, and you have you know, you have the, if you take 2 antipodal points, then the open semicircle will be, you know, from, you know, from here to here, and you know, and you have to remove those 2 points. When you say open semicircle, it means open arc, so the endpoint should not be included. So you take all points you know, along this dotted thing that I have drawn, and you forget these 2 points. That's an open semicircle, okay. And all the C intersection gamma points cannot lie only on this open semicircle. And why is that? That is because if they did, then what you could do is that, you know, you have this diameter, okay, and all you have to do is translate this circle a little upwards in a direction perpendicular to the diameter, and all these points will come inside, okay. And that will, if you do that, what will happen is that, you know, you will get a smaller, I mean, now gamma will come completely inside that, and therefore there is a smaller circle which will touch gamma and contain this, and that is you know, not allowed, okay. So if C intersection gamma, so let me write as P some I'll put some you know, if C intersection gamma consists of only points, consists only of points points such as R, such as Q, that lie on an open semicircle, PQR, okay, then one can slightly displace C perpendicular to PR and ensure that gamma gamma does not intersect C, okay, a contradiction, okay, because as I told you, it's very, very important, gamma has to intersect C, okay, because gamma intersection C is non-empty, okay, right. Therefore, the first claim is that the intersection of this circle, smallest circle which contains gamma, and with gamma, all the points of intersection cannot lie in an open semicircle. Therefore, what does it mean? It means that if you take C intersection gamma, it will lie in it will lie on an arc which is at least a semicircular arc with at least one of the endpoints included, okay, because if you remove both the endpoints you will get an open semicircular arc, and on such an open semicircular arc all the points of the intersection cannot lie. That's what the claim 1 says, okay. So claim 2, is thus C intersection gamma lies at least in a semicircular arc with one endpoint included, okay, and the other endpoint not included, okay, right. And you see and in this extreme case, so look at this extreme case, that the intersection of C and gamma, they lie in a half open half closed semicircular arc, okay. Look at that case, that is the extreme kind of case, okay. It can lie in something bigger, but the smallest circular arc on which C intersection gamma can lie has to be a semicircular arc with at least one endpoint included, okay. Because claim 1 says that if you remove both endpoints, it cannot lie in the in any open semicircular arc, all right. Therefore, you take this extreme case when C's intersection gamma lies on a semicircular arc with one endpoint included, okay. and you can take that one endpoint to be one of the intersection points, then you can see immediately that so I want to say the other the other end of the diameter, you see, that has to be the other intersection point. Okay, so I want to say that okay, so let me try to convince you. I am trying to convince you that the C intersection gamma has at least 2 points. Right? So that's what I want to say. See, you take the intersection of C and gamma, that is at least 2 points. Because if it is 1 point always lies in an open semicircular arc, and the C intersection gamma cannot lie wholly on an open semicircular arc by claim 1. Therefore, there are at least 2 points in C intersection gamma. C intersection gamma at least contains 2 points. That is point number 1. Point number 2, if it contains exactly 2 points, then these 2 points are antipodal. They are the endpoints of a diameter. Okay, and this, for example, will happen for an ellipse. All right. So so that's what I want to say. So let me write it correctly. Let me rub this off. So I think that's easier to. So I'll just put it as so claim 2. Thus, C intersection gamma has at least 2 points, and if it is exactly 2 points, then these points are antipodal points. Example is gamma is an ellipse. Okay, right. So now, so there are at least 2 points. Okay. Now, what I am going to say is that as you can see, so let me draw a generic picture like this. So I have a picture like this. So I'll draw. Okay. So you have so this is the C, and this is gamma. Okay, and there are, so you see there are the so this C C, which is the smallest circle that encloses gamma and touches it, mind you, so there are these points which I am interested in. These points are points of C intersection gamma. Okay. Okay. Oh, I see. Okay. Antipodal points are points which are the endpoints of a diameter. Okay. Diametrically opposite points. So let me mention that diametrically opposite points. Okay. So so you see, you look at this picture, all right, and you see let R be the radius of C of the circle, so the smallest circle that contains gamma. Then you write capital K to be 1 by R. That will be the curvature of C. Okay, and you can take it as the sine curvature of C if you traverse C in the anticlockwise sense, if you want. All right. Now look at these, look at these points, where C hits gamma. Okay, it's clear from the picture that the curvature at each of those points is greater than or equal to this capital K. Okay, so I get this point P0, P1, P2. Okay, and in general there may be more. So the thing is that if you take the curvature, of gamma at P0, okay, then this curvature of gamma at P0 is certainly greater than or equal to K. And similarly, the curvature of gamma at P1 is greater than or equal to K. The curvature and the same thing happens at every point where this gamma touches the circle C. Okay. Okay. So curvature of gamma at P is greater than or equal to K for every P in gamma intersection C. Okay. And but the proof of that is that if you take any such point and you draw the circle of curvature, that's going to be completely inside this C. Okay, so it should have a smaller radius, therefore it has a greater curvature. All right, and so there are these points. So let me label these points. So I have a K gamma greater than or equal to K, and here also I have K gamma greater than or equal to K. And here also I have okay. The claim is that there are points in between any two such points on C intersection gamma. There are points in between where the curvature becomes strictly lesser than capital K. Okay, so you are going to get these points, Q1, then Q2, and Q3. Okay, where the curvature at gamma at the Qi is strictly less than K. You are going to get points like this. There exists points like this. Okay, and this is kind of geometrically obvious, but needs a geometric proof to be written down correctly. Okay, which we will do. So so the claim is there exists points so between, so let me write it more accurately, between any pi any, let me put p comma p prime in gamma intersection C with there exists a Q belonging to gamma such that the curvature of gamma at Q is strictly less than K. Okay, so you can believe this from the picture. All right. So now you see we are literally done with the proof. See, what is going to happen is that you just look at the portion of the curve from let us say you look at the portion of the curve from here to here. Okay, and also the portion of the curve from here to here. Okay, so you see here at P naught, you see the curvature is greater than or equal to K. When you come to Q1, the curvature is strictly less than K. All right, and therefore you see the curvature is decreasing. Okay, it's going from values greater than K, greater than or equal to K, to values strictly less than K. Okay, and similarly, if you take this portion of the curve from Q3 to P naught, you see the curvature is going from a value strictly less than K to a value greater than or equal to K. So what this means is that the curvature function is increasing. So before P naught it is increasing, okay, and after P naught it is decreasing. All right, and so that means that between Q3 and Q1 there is a vertex. There should be some point where which is a critical point. I'm not claiming that P naught is that point, okay, but there is a point between Q3 and Q1 which is a vertex. Similarly, the same kind of argument is going to give you that there is going to be a vertex between P0 and P1, okay. Therefore, between any two of the Pi's there is going to be a vertex, and between any two of the Q's there is going to be a vertex, okay. Therefore, basically what you are going to get is going to get, if there are n of these P's, you are going to get 2n vertices. You are going to get 2n vertices, but there are at least 2 P's. The C intersection gamma is at least 2 points, so you will at least get 4 vertices, and that is a proof of the four-vertex theorem. Okay, it's a completely geometric proof. All right, so one just has to justify these things by geometry constructions, and then the proof is quite straightforward. So the claim, so for this claim, so I'll also write that. So let me rub this out. So let me write the next claim, which is the main thing, which is the claim is that the P the points so let me say consecutive points. So when you say consecutive points, you are traversing in the anticlockwise sense, okay. Consecutive points on gamma intersection C with the traversal on gamma being counterclockwise will have vertices in between them, okay, and so I want to say, so I have to label the points on C intersection gamma as P0, P1. So let me just start with P1 itself as P. I hope I have used P0, is it? That's bad. All right, so then let me stick to it. P0, P1, etc. Pn minus 1, okay, and the intervening points as so, and the intervening points as this, okay. Clearly between every Pi and Qi plus 1 there is a vertex. Then you have claim is between any successive P's there is a vertex, and between any successive Q's also there is a vertex, okay. Thus there are at least 2n vertices. Thus, so between any successive P's there is a vertex corresponding to a local minimum and between any successive q's also there is a vertex corresponding to a local maximum. So that is important. Local. Okay. So thus there are at least two n vertices. Okay. But n is greater than or equal to 2. Since the intersection of C and gamma is cardinality is at least 2, as we have seen. So this implies that there are at least 4 vertices. And in fact these vertices are alternately they are points of local maxima and minima. And these are alternately points of local maxima and minimum for the sine curvature for the curvature of gamma. Okay. So you see this is a proof which is completely geometric and doesn't really involve anything complicated. So this is a this is more of a geometric argument. All right. Now you can ask the converse to this statement, the four-vertex theorem, namely if you have a continuous curvature function, okay, on a closed bounded interval, such that the you have on the end points it is the curvature function is the same, and also continuity is there at the end points also, then is that the curvature function of a simple closed curve? Then of course you see one necessary condition is that it should have at least 2 local maxima and 2 local minima. So you can ask that if you have such a function, is it actually the curvature function of a simple closed curve? And the answer is yes. And the proof is quite involved. Okay. So the converse is the full converse of the four-vertex theorem is also correct. Okay. So I will just state that. So remark the full converse to the four-vertex theorem holds. So theorem is converse to the four-vertex theorem and that is if k from closed AB to R is a continuous function with k of A is equal to k of B, and k has at least 2 local maxima and 2 local minima, then there exists gamma simple closed smooth curve in R2 such that the sine curvature of gamma is exactly k. Okay. So this is the converse, and the converse holds, and the proof is involved, and it involves more use of differential geometry. Okay. So we will not get into that, but the converse is true. and starting from the convex case of the four-vertex theorem proved by Syamadas Mukhopadhyay to this final converse, spans about 100 years of research in these kind of questions, and still there are unanswered questions here. Okay, so I think I will stop here.